PFAS are called forever chemicals because they are persistent, but persistence is only part of the challenge. What makes PFAS uniquely difficult is that they continuously move through the water cycle. PFAS contamination is not a single source problem anymore. When we say PFAS, we're actually referring to thousands of different compounds. Traditionally, attention focused on long-chain PFAS such as PFOS and PFOA, but industries increasingly shifted towards shorter-chain PFAS. So today, the challenge is no longer just about a few chemicals. It is about managing the entire class of highly persistent substances in an environment where regulations, analytics, and treatment technologies are evolving simultaneously. The good news is that the progress exists if active effort continues, reducing emissions, reducing use, and limiting discharge into the environment. Regulators are now shifting from simply identifying PFAS to actively managing risks, which includes monitoring PFAS in the water system, increasing industrial reporting obligations, and discussing broader PFAS restrictions and bans. At the same time, permitting is becoming more case-specific and risk-based, but this creates challenges. Some protection goals are already below environmental background concentrations in certain regions. So regulators, industries, utilities are all trying to answer the same question. How do we make scientifically sound decisions when the thresholds keep evolving? That is why PFAS monitoring strategies are evolving beyond simple compliance testing. Monitoring involves several layers. Defining what to monitor, designing robust sampling frameworks, selecting analytical methods, and moving towards continuous or online monitoring. Traditional target analysis remain essential because it is standardized and accepted for regulations, but it only measures compounds we already know. And this is where non-target analysis becomes important. NTAs explore the unknown chemical space. It allows scientists to detect previously unrecognized or unregulated substances, including transformation products that form when chemicals break down or react in the environment. This is especially important for PFAS, where many compounds remain unregulated and poorly understood. And finally, once PFAS are detected, treatment becomes the next challenge. Most current approaches follow one principle. First concentrate, then destroy. Technologies such as activated carbon, ion exchange, membrane filtration separate PFAS from the water efficiently. But separations only transfer the contamination into the concentrated stream. So additional destruction technologies are needed. But the biggest shift is not only technological, it's also strategic. PFAS are forcing the water sector to rethink how we manage persistence, uncertainty, and accountability. And in the end, the question is not whether PFAS are forever. The real question is how quickly can we redesign our system before forever becomes the cost of inaction.